I'm Mike Levis with the Mount Hood Ski Patrol Avalanche Program, and today's topic is avalanche nomenclature. We're going to discuss the language of avalanches and the different types of avalanches that you may encounter. Our goal in this module is to give you the tools to identify the types of avalanches you may encounter and to assess the risk based on the type of avalanche. So let's start by running through briefly the kinds of common types of avalanches you'll encounter. Let's run down the list and we'll dig into each type in a little more detail. Loose snow avalanches. These are quite common on Mount Hood. The pinwheels of snow you see rolling down the mountain are the beginnings of a loose snow avalanche. Slab avalanche. These are the most destructive kind of avalanche. These are the ones you typically see in all the YouTube videos online. Cornice release. Strictly speaking, these are not avalanches, but are a common natural trigger for avalanches. Ice avalanches. Ice avalanches are very common higher up on the glaciers where seracs can break loose. Wet or slush avalanche, very common in the spring. Typically slow moving, but can contain a lot of mass. And last but not least, roof avalanches, which are common on all structures on Mount Hood. Let's start by looking at loose snow avalanches in more detail. Loose snow avalanches are characterized by a point release that initiates a small slide. As the slide propagates, the point release expands into a fan-shaped slide. Loose snow avalanches are surface phenomena. They start on the surface and typically involve only surface layers of snow. Loose snow avalanches are typically not dangerous. They do not contain a large mass of snow and do not have a large release of energy. So let's talk about slab avalanches. Slab avalanches are the most destructive form of avalanche. As the name indicates, slab avalanches require a cohesive layer over a weak layer. A trigger, natural or man-made, causes the weak layer to fail. Since the weak layer is buried in the snowpack, failure of the weak layer results in a block of snow releasing downhill. The failure then propagates and releases a large mass of snow and a lot of energy. The slide quickly accelerates to 80 miles per hour or greater. These are particularly dangerous to people because of the failure propagation. You may actually be above the failure point, but the propagation can be uphill, resulting in a slide that actually starts above you. Cornice release avalanches are triggered by a cornice failing. Cornices are large, overhanging snow structures on the leeward side of a ridge. When these cornices fail, they can be large enough to be an avalanche themselves, or they can trigger a slab avalanche on the downhill aspect of the hill. Consider the image on the left of this slide as a cross-section of a ridge. The cornice can actually extend for many meters in each direction. Also note that if you're approaching the ridge from the windward side, right here, you cannot tell if there's a cornice present or not. Cornices are quite common on Mount Hood. For example, in the canyon above the climbers' parking lot at Timberline, you'll often see a cornice. Note that the cornice can actually break off well to the windward side of the ridge. You could break off in this zone right here. So anyone traversing the ridge can be swept down the hill in the event of a failure. The message here is always assume there's a cornice when approaching a ridge and stay well back from the ridge, from the edge. Ice avalanches occur on glaciers where seracs, which are large blocks of ice, break off and slide down the hill. These avalanches tend to occur at places where the glacier ice flows over a steep slope or cliff band. The increasing tensile stress results in the calving of large blocks of ice that then fall downhill. Collapse of a glacier seracs has caused many fatalities. Note that since these failures are due to glacier creep and tensile failures, they can occur at any time of the day or in any season. Travelers should avoid crossing below or camping below areas of potential icefall. A wet or slush avalanche commonly occur in the spring with the onset of warmer temperatures. As the temperature increases, The bonds holding the snow in place weaken, and slides can occur. These are typically slow-moving, but can contain a large mass of snow. Note the dirty brown appearance. These avalanches will typically carry a lot of sediment with them since the bed surface is typically the ground. These avalanches can be dangerous if the large mass of snow could potentially push you over a cliff or some other objective hazard. Roof avalanches happen at all the resorts on Mount Hood. These are particularly dangerous because they can bury people who least expect the hazard. Victims will typically not be wearing beacons. In many cases, the resort may not even know that someone is buried unless it's witnessed, so there may not even be a rescue attempt. In the event of a roof avalanche, you should assume someone is buried until proven otherwise and begin a search. So let's shift gears now and talk a little bit about the language of avalanches. This slide shows the anatomy of a slide avalanche. The top of the slab is the crown. The crown is right up here. The bottom of the slab is the stalk wall. The sides of the stalk wall here. The sides of the avalanche are the flank. The vertical surface of the remaining snow above the avalanche is the crown face right in here. This is where the crown was attached. The path the avalanche follows is the track. The surface remaining after the slab has moved downhill is called the bed or bed surface. So this would be the bed surface right in through here. Here's the track, the slide path of the avalanche. Here's the bed surface. The area where the slab avalanche accumulates at the bottom of the track is the deposition zone or runout. The toe of the avalanche is the farthest point of travel of the avalanche debris. Think about these features of the avalanche in terms of a rescue. Where would you start looking? Where would you not spend any time looking? Are there any hazards to the rescuers that you need to be aware of? We'll talk a lot more about this in the companion rescue section. Here's another view of a slab avalanche. You can see there's the crown and the crown face where the fracture line was. Here's the flanks over here, and the stalk wall. It's difficult to follow because the slab has shattered, so a lot of times the stalk wall will be difficult to identify. So in order to have an avalanche, you also need a trigger. Trigger events can be natural or man-made. Natural triggers can be a cornice collapse, ice fall, earthquakes, or rapid loading from snow and rain, or rapid temperature change. Rapid loading from snow or rain is the event we tend to be most concerned with. Rapid loading adds weight that will stress any underlying weak layers. Note rapid loading can be due to wind-driven accumulation in addition to precipitation. We'll talk more about this in the weather module. Man-made triggers include avalanche mitigation activities such as cornice drops and various kinds of explosive, as well as triggers from human traffic. This includes skiers, climbers, and snowmobilers. Note that most avalanche accidents were triggered by the victims. When an avalanche occurs, they're classified by several key parameters. They're classified by type, slab, loose snow, etc. They're classified by trigger event, skiers, earthquakes, snowmobilers, and they're classified by size. Size is measured both in terms of the physical dimensions of the avalanche as well as the destructiveness of the slide. When you read avalanche reports on NWAC or other avalanche sites, you'll see these parameters used to describe the avalanche. So when we talk about the size of the avalanche, one of the parameters we use is the avalanche size relative to path. You should interpret this as the size of the avalanche relative to the possible area that the avalanche had available to slide. And you can see the scale ranges from R1 to R5, where R1 being the smallest and R5 being the largest. This slide, this size scale could be found in the SWAG manual published by the American Avalanche Association. And if you move on and take Avalanche 2, you'll become very familiar with the SWAG manual. This slide shows the scale for avalanche destructiveness. These numbers are pretty staggering. You can see it starts again, D1 being The smallest avalanche, less than typical mass, less than 10 tons, typical path, 10 meters or less, all the way down to D5, which is it's a staggeringly large avalanche, 1,000,000 tons of snow coming downhill over a 3,000-meter path length. Wouldn't want to be caught in that one for sure. And these slab avalanches can be terribly destructive. This slide shows some of the damage to buildings that can occur, and certainly if there were people in these buildings, they would not have fared very well. Which brings us back to our friend, the avalanche triangle. Terrain. Is the slope steep enough to slide? Snowpack. Is there a consolidated layer over a weak layer? Weather. Has the weather been changing rapidly as in new snow over a short period of time to increase stability? And what will the trigger be to start the slide? And that's it for our module on avalanche nomenclature. Thanks all for listening.